the same thing, but even worse.
But then you don't have to show up to the class like at 4:30.
True, it wasn't lecture about anything.
Yeah.
So how is it gonna be? You've seen him in regular class.
All right, guys, let's get started. Good morning. Welcome back. Super early. The best. Yeah, welcome to Geotech. Sweet to see a lot of familiar faces and a lot of names on there. Again, I just want to throw this out there. I did not choose this time, so please don't hate me for that. I'm very sorry. And I did not choose the final time either. But we'll try to, all I can say is keep an eye on the Canvas, download the mobile app, put your little notifications on or whatever, because if stuff comes up and like we're able to condense some of the lectures into one lecture, then I could just cancel one of the classes in the morning. So keep an eye on that and like just check it before you go to bed so you don't wake up super early and come here and nobody is here. Yeah, and I also apologize for the dual screen. I don't know which one I'm going to look at, but pick whichever one you want. Everyone was able to get familiarized with the Canvas page and stuff so far? All right, it's pretty much the same thing, same format as last semester for CE materials. Canvas will be where I post all the lecture notes ahead of the class. I'll post them by 5 p.m. On the previous day. And that's where we're going to be having all our quizzes and everything. There's no quiz this week. A lot of you guys have already done the introduce yourself, so be sure to complete that. If you haven't, that's going to be like that attendance check for this week that all professors have to do for the academic tracking and that kind of stuff. But yeah, no quiz this week, but generally throughout the semester, we'll have a quiz each week due by 5 p.m. or sorry, midnight on Friday. Also, heads up, I still haven't gotten my dates right, so that's just something I'm still going to be messing up this semester is dates. I'm going to call this probably a Wednesday class like 20 times. So just a heads up with that. All right, Geotech. I like teaching this class and I like the fact that it is right after CE materials, because if you remember our CE materials class, that last kind of couple weeks we talked about geomaterials. And that was kind of setting up and really like just leading into this course where we're going to go into more depth of what geotechnical engineering is and how we can use soil and how we can design soil as a construction material, but also as a foundation, for structures and other types of things. So a few week one reminders. Again, there's no lab this week, which everyone knows because labs are already over. There's not going to be any labs next week too. So if you check the syllabus, we'll start labs in 3 weeks. Week 3, sorry. And it's going to be pretty much identical to the CE materials class. So if you didn't have me for CE materials, you should have a separate Canvas page for the lab section. If you click on that, you click on people, then you'll see your lab group. Those are all just randomized. I do that just to simulate the working condition where you don't always get to choose who you work with on project teams. So you still have some time to communicate with your lab groups, and I'll go over more details that first lab week on the expectations for the lab reports and all that stuff. But yeah, no labs this week and no labs next week, so we still have some time for that. Yeah, the introduction on Canvas is the only thing new this week. Again, a lot of you guys have already completed that, but make sure you complete that by Friday at midnight if you haven't already. This is our textbook. I forgot to bring the other textbook in, the actual physical copy I have. This one is cool because it is offered free through UNF Library. So on Canvas, you should be able to click a link, and if you're logged in to your UNF account or your library account, it'll take you automatically to the ebook version of that. Just a heads up, you can't download the entire PDF. They have like a limit on the page numbers that you can download. So if your computer is really good with internet, you may not need to download anything, but if it's like mine that loses internet every other day, try to be strategic with which PDFs you want to download, or just wait and then wait for the material that we cover and then download that to reference and have on your personal computer if you want. There is another textbook that I recommend. It's Holtz and Kovacs textbook. It was in the lecture from Tuesday, and it's really solid and it's pretty cheap. You can find like older versions of it online. There might be some versions for rent in the PD or in the library too, if you're interested in that. I definitely recommend getting that textbook if you're interested in geotech. It's just solid for basic geotech all the way to like foundation design and stuff. So if you have a few extra money laying around, then buy that textbook. It'd be helpful. Yeah.
The 100-page limit, is that still every time you click on it?
Oh, no way.
So you can just open.
Sweet. Okay, that works good. I don't know why I didn't try that. That's so sweet. Okay, so if you guys didn't hear, yeah, you can download, even though there's a page limit for when you download that, if you reset the browser or just open another browser, then it'll reset. So you should be able to download the PDF as many pages as you want for that. All right, a few other things before we get started into some material. I've talked about this before, but if you aren't involved in like a student club, especially an engineering organized one, I'm a little biased because I'm the faculty advisor for ASCE, but there's a lot of opportunities out there. ASCE has a conference for the 25th through the 27th. It's over in Tallahassee. It's actually an in-person conference, and there's a lot of cool competitions and other just networking events involved with that. ASCE is solid, but there's also plenty of other ones. What's the one? Ship. Okay, not Albanian ship, but ship. But yeah, that's another solid one. I know you guys have some conferences and stuff too. So just want to encourage you guys to get involved. UNF is sweet because it's a tight knit, like smaller student body. So there's lots of opportunities, and a lot of these people you're going to be working with if you stick around in Jacksonville, like for years to come. So might as well get to know each other and get to learn how to work with each other now while we're in class. So if you do have questions with ASCE, you can reach out to that email, reach out to Brody. I'm sure Tess is okay if you reach out to her for any more information too. So yeah. All right, so what do we know about geotech and just construction in general, right? We've talked a little bit about this in our materials class, but before we build something, let's say like ShadCon finally wants to build that cool downtown area where we can actually use downtown. What kind of things do engineers need to know about a area before we build stuff on it? You can just shout stuff out. I know it's early, but just feel free to use your voice. Any ideas? Yeah, so yeah, that's cheating because that's geotech stuff. But yeah, soil / geologic conditions definitely is important. But what else? Elevation. Yeah, so that's kind of like in the geologic conditions, but yeah, elevation, especially in Florida where we have like groundwater table issues and flooding. You need to check the FEMA maps and everything. But like also like our structural engineering friends. So structural loads are important. We need to know what type of structure it is and how these external loads are going to be applied and eventually transmitted into the soil or whatever foundation we have. The serviceability is important. So what exactly is the structure used for? As you guys may have already seen in some of your workplaces, depending on the type of structure will be dependent on the type of or the amount of money that you pour into it as far as design considerations go. If you are designing a nuclear power plant or something that is supposed to be like there for a long time and produce a lot of energy or output for society, then you usually put much more design effort into those types of structures than you would for like a warehouse or just a storage unit or something like that. So the serviceability of the structure is going to be an important aspect. Other things like existing utilities. And then as we were talking about, like, sorry, it still doesn't work. That's an L. Whatever. As we were talking about with in the CE materials class, also something you would consider is the available contractors and the available materials around, right? Like, so availability of materials or contractors. I was talking to one of the other students who I had previously who's working right now, and they've been doing a new geotech type of what's it called, ground improvement technique. And the contractor, like when he mentioned this, I was like, oh, I'd never seen anyone do this in Florida. And he said that the contractor drives 15 hours from South Texas, like just because we don't have the availability of contractors in this area. So that's something that, it's kind of hard to replicate in the classroom, but when you start working, you're going to have to take that into account, like the availability of the skills of the nearby contractors or even the materials that they can use. So all this to say, like, you can probably see like there's two things here, maybe three things that we're going to focus on a lot in this class. Of course, the soil and geologic conditions, this being called a geotechnical course. We're going to be focusing a lot on this, but also the serviceability and existing utilities. So these are part of design considerations for geotech, but also the subsurface and the site investigation. So one of the roles of a geotech that we'll see throughout the semester is determining what is underground currently and how we can design what is above ground safely around what is currently underground. So we already have talked about this previously in the other class, but just to recap again, civil engineers, kind of just like a broad definition, it would be the management and design of infrastructure. So the infrastructure is a set of fundamental facilities and systems used to serving a society. So again, broad example, but some of these examples would be things we use every day, right? So utilities, roadways, bridges, transportation. I said this in the materials class. Basically all the things that we use every day without knowing we use. That's going to be one of the goals of a civil engineer, to design and ensure that it sticks around so we don't complain about it as citizens, right? Now, all these things have something in common. They're all constructed on or within the Earth's crust, which is kind of cool because that's where us geotechnical engineers come in. So we have to find a way to connect all of these things that are constructed above ground and rooted in the soil. So we have to have a science that explains the mechanics of the rocks and the soils, the response to the loading of these external structures, and how they can stay above ground and not sink or fail throughout the lifetime of their project. So the infrastructure generally, I talked about this in CE materials again, but these decisions for the infrastructure is based on two things, and that is based on safety and, of course, economy. So we can over-design something and make it as expensive as we can, and it'll be safe and stick around for thousands of years. But is that going to be the most economical thing? I.e. the Romans, like they over-designed the heck out of everything, and that's why all their structures in Rome are still sticking around. So just massive, and they cost a lot of money. So nowadays we don't do that because we know we don't have unlimited amount of money to conquer people and all that stuff. But as a geotech, who can think of some of the structures, or like the infrastructure that a geotechnical engineer would be specifically in charge of or involved in? You can just shout it out again. Subways. Yeah, that's really true. Yeah, tunnels or subways. Unfortunately, we don't have that here. Does anyone ride that little metro thing downtown that just goes in a little circle?
It goes like 2 miles. I see it sometimes, there's nobody on it.
It's like our claim to fame for public transportation, really getting there. Yeah, but yeah, tunnels and subways everywhere else besides Florida and the US in general, we have those issues. Somebody else said something.
The dirt stuff with the bridges we talked about last semester.
Yeah, like embankments and stuff. Yeah, embankments or MSC, those are called, MSC walls. I'll just put that here, MSC. So that's using soil as like a construction material. Yeah, that's a big one. Dams. I think that's how you spell it. Construction material. Yeah, other stuff too that we don't really think about. Landfills. All the stuff we throw away, the geotechnical engineer needs to ensure the site conditions before we stack a bunch of trash on top of it is conducive to support that trash, but also that if something happens, then we don't get leaking into the aquifer or any of the groundwater tables that we get our water from. And then of course, like the most common thing, foundations. All structures need to first have a solid foundation that the infrastructure or the outside structure can then be constructed on. And some of these high bridges or some of these large skyscrapers need to have pretty diverse or complex foundations to transmit the loading from the above ground structure safely into the soil so that structure doesn't collapse in on itself. So we've kind of talked about like two aspects of it. And basically what we're going to be learning about like throughout this class is that load transfer into soil. So you'll see through this whole semester, geotechnical engineers and structural engineers work a lot hand in hand. Not only do structural engineers help us design our foundations, like the concrete and the piles and everything, but also we need to work with the structural engineers to know how large or what size loading this structure can support, but also how that's going to be transmitted. So where these columns are like this, and like, you know, the external, the components, the kind of the shell of the structure. So these load transfer into the soils, obviously we need to, if we have a load applied to a soil, we need to know how the soil will react. So just like mechanics of materials, where we learned how if you twist a piece of metal, how much will it respond? If we pull a piece of metal, how much will it respond? We also need to determine that for soil. And the issue that we'll see is soil is a natural material. It's not something that we make. So it's much harder to define its response to loading. So what we call, just like we call mechanics of materials like construction, everything, that how the behavior, the soil will react, so behavior to loading, is what we call soil mechanics. And this is kind of the root of geotechnical engineering, is understanding the soil mechanics and understanding first how the site-specific soil will react to the external loads that we apply. So the theory of soil mechanics, we will barely get into it. We're just going to kind of scoot the surface, because you can go, or as you'll see throughout the semester, soil mechanics just as a general kind of genre of engineering is relatively young. You know, we're still understanding how soil will react in different areas and on a unified scale. But that's going to be kind of the basis of this class, and then we'll move up into like more of the structures that a geotechnical engineer would be involved with. So I want to summarize kind of the role of the geotech into three things. So first and foremost, the role would be to investigate. So again, my goal for this whole class is to sell you guys on why geotechnical engineering is the best. So I am a little biased, but geotech is a little interesting because we get to see the project from start to finish. We first have to investigate the site conditions. So we need to understand the specific soil conditions. We need to assign design parameters. So this is where that mechanics comes in. So just like steel has a Young's modulus, that E value, just like we have steel having a sigma Y, that yielding stress, if you remember from last semester. And you have all these design parameters that help us mathematically estimate the response of the structure or the material. We also have these for soil as well. So understanding the design parameters, that's the first thing. And I want to put, like, not only do we need to investigate, but we need to investigate, I don't know if this is the right word, but smartly. Is that a word? So as I said before, like, we can pour as much money into a project as we want. We can know the entire subsurface condition, you know, from ground surface down to bedrock for every square inch. But of course, that's going to cost a lot of money. And is that worth it as a geotech to pour that much money into a project where it may not require that much? So smartly, money-wise. So investigate, so doing a smart investigation and an effective investigation to understand the site conditions. The next one, of course, is then we have to design. That says design. And this is where we will work with the structural engineer. So in this class, we aren't going to get too much into the design of foundation types. That's going to be the tech elective that I definitely encourage you guys to take after this. But still, anticipating the most probable soil failure type is going to be key. Steel, we kind of know if we pull steel, it's going to break in tension, right? But for soil, loading the soil can result in different types of failure mechanisms. So first, understanding which type of failure mechanism is most prevalent at the soil type at your site, and then designing an effective foundation to transfer those structural loads safely through that soil so we don't hit that criteria of failure. And then during the whole process, the construction, we get to hang around during the construction too, which is fun. So not only do you get to do the site investigation, come into the office and work on the analysis and the design, but then we also get to ensure that the foundation is being installed and constructed correctly. And the big thing with this is because changes will happen. Again, what we're working with here is natural material. So unlike steel, where we can call up our steel making friend and say, hey, I need steel that has this certain strength, or concrete, where we can call up the concrete maker and say, hey, I need concrete that has this certain strength. We are working with what is given to us. So it's almost a backward side of analysis. We need to first understand the strength of the soil at our site, and then how much structural loading we can apply to that, and then how that structural load is transmitted through so it doesn't fail. So a lot of changes will happen throughout the project. So we need to work with the owner, the land developers, construction, and the structural engineers during that whole process. So you get to see the whole thing from cradle to grave. Well, hopefully not the grave, cradle to it's a finished construction project. Okay, so let's look at a little cartoon here. So let's say you wanted to build a building here. The contractor owner will hire a geotechnical engineering firm to perform the initial site investigation. So this is if it is just a natural terrain. What we would call here is virgin terrain. We use a lot of weird words in geotech, but this would be virgin terrain where nothing has been constructed. We can assume everything under the ground is natural. There's no existing man-made structures or anything like that. So basically what a geotechnical engineering firm would do, they bring these trucks out. Maybe you've seen these on the side of highways before, or maybe you've worked with them on a project before. But these are basically drilling rigs, and there's different types of tests that can be performed. But long story short, we're bringing samples from underground up to the surface, so we can then bring those samples into the lab and do different tests on those samples. And those are the tests that you guys are going to be doing in this class. So what these do is normally collect samples every 2.5 feet or so. So, right, if a drill rig came in here, we'd poke a hole down, we'd reach a certain depth and have these soil samples with depth. And then we'd be able to identify the different layers. So the geotechnical engineer will then characterize the site and determine these soil layers. Obviously, it's expensive and these tests take time. So to come out here and do a test every 5 feet or so is not going to be economical. So this is where that discernment of how many tests are required comes into play. And that's where like the local aspect and understanding the geologic conditions is really important. So generally they would do a few tests per site or so, and then they determine the typical or the characterized site to determine these soil layers. So what we'd do then is draw a little profile, and we'd be able to say where the limestone is throughout the site, or where the bedrock, where the different soil layers are underneath our project site. So that next step then would be to add these strength parameters. So again, thinking back to mechanics of materials, steel has these parameters that help us design against them, right? Like concrete has a compressive strength, that FC value. Again, it has the Young's modulus, the E, the sigma Ys, the sigma Fs. So soil, we need to define characteristics for that, even though they're a little different. So some of these will look like this, and you don't know what these are yet, and that's okay. We'll talk about these throughout the semester. But we need to define these strength parameters, and this is where the lab consideration comes into play too. So we do tests on the samples in the lab. We'll come back and be able to create a profile like this. So then we talk about, get back with the structural engineer and determine what type of foundation, or if there is an excavation that needs to be performed for this. So let's say they need a basement and we need to install an excavation for this. So there's different types of retaining walls or other types of geotechnical designs that we would then construct and work with. Again, we don't see many of these in Florida, but stuff like this, where we lower the groundwater table and we lower the ground surface elevation so we can then get more room for the structure to build our parking garage or whatever they need underground. Again, Florida doesn't have many of these because the high groundwater table and just poor soil conditions. But if you've ever been in any other city and seen construction, you've probably seen something like this. And this would be a role of the geotech. We have something similar, which we talked about in our materials class, right? Like a retaining wall, or what this is called is an MSC wall, the mechanically stabilized earth wall. And again, this, even though it looks like it's concrete right here, these are just little panels. If you were to remove those little panels, then the structure would still stand up fine. It's just, to not freak people out and see just soil stacked there. But this is using the mechanical properties of soil as a construction device. So instead of pouring concrete and putting this whole massive thing with like steel or concrete, we can use earth. And it's basically the same thing as a retaining wall. So let's say we've already constructed the retaining wall and everything. Now we need to design what type of foundation. Has anyone worked with foundations before or anything? I know you probably have, everyone. But we'll learn throughout the semester there is two main categories of foundations. So what we'll first have is our shallow and our spread foundations. Basically what these are doing is we're taking this structural load. So this is that structural load. And we are distributing it throughout the soil area. So this would be a footprint, and we would then apply a bearing pressure instead of a single point column load and distributing that across everything. Just like if you took a pen or something and you poked your hand, that pen, since it's a concentrated point, will hurt a lot more than if you put a coaster or something on your hand and then poked it. You're distributing that load and you're decreasing the pressure by increasing the surface area. So again, that pressure, what we'll show that as is generally a stress, so a sigma, and that is equal to our force divided by our cross-sectional area. So if we increase the cross-sectional area, if we increase that denominator, then we are decreasing our stress. So with these types of structures, what we'll see is we will apply a bearing pressure, and the soil will have what we call a bearing capacity. So then it's pretty easy math-wise. As long as our bearing pressure is less than our bearing capacity, as long as the load that we're applying to the soil is less than what the soil can stand or withhold, then we shouldn't have any failure. And in structures, we copied this from a lot of people. You could probably, or just basic, nature, or just what you guys have probably been able to witness in your day-to-day life. If you walk on the beach and so the soil, is compacted and everything, then maybe you'll have a small footprint. There'll be little deformation. Some places though, where the soil is really loose, then even though you weigh the same amount and you're not applying any more load, you may sink and the soil may move a little bit more. And of course, in areas where the soil is really crappy, you can't see, but that dude just sinks into the ground. So not only is it a structural consideration of how heavy or what that loading is, but it's also a soil consideration. And that's why people do that in every place besides Florida. You distribute the loading so you don't apply as much of a bearing pressure, and then you're able to stay on top of the surface. So that's our shallow and our spread foundations. And generally, a lot of structures in Florida, just your standard house, your standard, just normal average structure will just use this type of construction and this type of foundation design. The other one though, in areas where there are really poor soil conditions or extreme loading, we would use piles, or these are called our deep foundation. So piles or drilled shafts. They're also called caissons if you work in other countries. They're called that. So I'll just write that. I think it's spelled like this, 4 S's, caissons. And basically instead, what we're doing is instead of applying all that soil or that pressure at the surface, we're now distributing it vertically. So now we use friction along these piles and we transmit the load to a denser or a deeper soil layer. So if you ever go like out on the beaches or anything, or out like in the Swanee River, you'll see a bunch of these houses on piles, and that's also against flooding, but it's also to distribute that loading from the house to a stronger layer that's not the ground surface, because we don't trust the layer at the ground surface. So these are also something that you may see driving around, especially if you live over in the Orange Park area or that where the FCX is, the First Coast Expressway. They're putting a bunch of piles in like that. And these are the foundations that are getting buried so they can put the bridge on top of it. And so that bridge won't settle down or settle. So let's just say our little whatever project, the Wawa, you guys don't have Wawas up here, so it's not that big of a deal. But in Orlando, there's like 6 new Wawas.
We got plenty.
Plenty?
I ate there last night.
All right, well, tell me where they are. I only know of one. So.
Yeah.
Okay. Sorry. No, didn't mean to strike a nerve with the Wawa. I thought you guys were gate people, but I guess not. Whatever. All right, so let's say we have this, and they decide to do on piles instead. So this, again, if you remember, this whole like illustration here, this little cartoon was in virgin ground, right? Like this is land, a nice prairie that nobody's constructed in. But of course, 9 times out of 10, you're building in an already industrialized area. So we have to worry about other things. We have to worry about near existing tunnels or utilities, other buildings, water or docks, all these things that we have to consider how the loading from this structure is going to affect existing loads. If you've ever gone to New York City or like Chicago or like the 2 old cities in the US that we have, you'll notice like it's built in layers, right? So some of these new structures are being constructed over layers of existing structures. Some of those structures are so old that they're not even documented. So the type of subsurface investigation is really, really important. So we can ensure that as we're drilling one of these piles down, we don't accidentally poke an existing subway or a gas line or something that is going to cause much more damage underground. So what happens if the subsoil investigation or design isn't correct? So if we think this is what the site conditions look like, because we did a few tests here. So this would be like test, and then test, and we just interpolate and we assume, okay, the soil layers are like that. But what would happen if it's not really like that? Like we have to, again, ensure that we're doing a robust enough subsurface investigation that we are not missing any anomalies or anything like that. And the big one in Florida is our sinkholes. Like we have a certain type of limestone bedrock that is conducive for internal erosion. And if we accidentally miss one of these little pockets of subsurface loose soil and we put a building on top of it, then you guys have probably seen some of the articles and the news people come out and freak out about it. But this is all because the geotechnical engineer or whatever the geologist doing the work missed a section of vulnerable soil and decided to construct a building over something that they didn't know was there. So this one was the Disney Resort in 2013 in Orlando. And luckily, like this one didn't have any casualties or anything. They were able to notice the structure creaking and evacuate the building before it collapsed in. There's a bunch of other stuff. So like also not only could we miss a certain area, but what happens if we bring it to the lab and we do all these design checks and then we calculate those design parameters, but they end up being all wrong. So then you have stuff that happens like this. And this probably looks familiar, this type of structure, the Leaning Tower of Pisa. This is actually due to a poor geotechnical engineering design. They didn't know that the clay was as thick as it was under a certain corner. So that weak soil actually caused it to settle that way. Unfortunately, like good for them, the geotechnical engineer kind of scooted it because he was like, oh, now it's a famous landmark. But most of the geotech problems don't become famous landmarks. So don't follow this mold if you're an engineer. Try to design something that won't tilt because you'll probably get in trouble. But let's look over some of the other geotechnical design failures. And I just like showing these because, again, geotechnical engineering is a very important a very important discipline of civil, but it also doesn't get the most credit because you don't see the work that they do, right? Like all the work is buried, it's all underground, and then the fancy structural engineers come in and take all the credit. Not bitter at all, but still, like the failures are then placed on us, and we have to ensure that we're doing a good enough job, because the stuff, like, you know, that's probably the most important part of the structure is the foundation. So you could have failures like this. This is a bearing capacity failure, and it is actually hard to see. But what happens is this structural loading ends up pushing the soil up this way. And so we have this soil mound that is heaved up. So this is just like if you were to go to the beach and it's really loose soil and you step really hard on sand, what you'll actually see is around the perimeter of your foot, the soil rises up. So that soil doesn't just settle down, but it actually moves to the side. And that's actually what happens here in this type of failure. And of course, this is earthquake induced too. But other stuff like this is a hill that we don't have these in Florida, but this is a hill, and it's like where the elevation goes up. And, you know, if we don't design the slope correctly, then it could fall over and obviously block a major I-4 road, which would not be good. And we do different things to combat this. You know, there's other types of disciplines where this is, again, similar to the retaining structures, where we put these nails in to hold back the soil so we can cut it and it won't fall over on the road like this. So this one is in Taiwan. You can look up more details of that too. This is a kind of a sketchy example. This is in Dubai, and we'll talk about some of the material properties. The permeability of the soil is going to be really important. A permeability, just long story short, is the ability of the water to flow through it. So if the water can flow through that soil too quickly, then we can have intrusion of water into our excavation like this. So although this excavation looks good here, if you zoom in right there, you can see there's one area where we have some water actually flowing through. So this excavation, actually, this is all water right here. So the problem with water is when we start having water flow through it, it increases the erosion. And then it's a progressive thing. So eventually this whole thing flooded, and now you get, instead of an excavation, you have a nice little lake with the crane sticking out on the top. So again, like one little detail of misdesigning the permeability of a structure or the permeability of the soil, or just the construction aspect, could have like extreme consequences and completely ruin a project, like we see here. Other simple little things. This bridge, this one is in Minnesota, I think. You can have a perfectly designed bridge. Everything works structurally, but you can see here one column, one structural column settled more than the other ones. And even if it's only settled like a couple inches or like, you know, half a foot or so, that could have dire consequences on the serviceability of the bridge. So everything else is fine. The whole bridge works, but this could have been a geotech investigation where it settled down. Yeah.
How are they going to deal with that?
Yeah, that's.
Or how did they deal with
So
that?
what they would end up doing is you can jack up a foundation. So a foundation is sitting on soil. You can come and put other piles near it. And then with these really heavy things, it just, or like jacks, basically you jack the whole thing up in stages. So, I mean, it's not the worst. It's not as bad as the other one, the excavation, but still, like, this is added costs, and it could have been easily avoided if they had just done an investigation in that spot and maybe noticed a weak soil or some type of anomaly there. So again, I showed this in the last lecture, but just one of the most interesting things about geotech is it's very diverse, just location wise. You know, like the US, this is a geologic map. So every single one of those colors is going to have a different geologic condition. And then every country you go to is going to have a different geologic condition. So if it has different soil conditions, it's going to have different design considerations and other problems associated with it. So as I said in the first lecture, if you work in Florida as a geotech and you get bored after like 10 years, then you can just move to a different state and then you got to start from scratch. So it's kind of nice, like a lot of variability, and it's a lot of involvement and a lot of communication within the geotech community. You know, like if we have a project in Montana, I'm not going to do the design there. I'm going to call a geotech in Montana who knows the local area a little bit more. So I wanted to end too by showing some of these videos. I don't know if it's going to load. Ooh, cool. Again, the big area in geotech that I'll be focusing on a lot in this semester is the site investigation and the problematic soils. So first, the most important thing is understanding the mechanics of the soil at your project site. And a unique geologic phenomenon up in Norway, if anybody's seen this stuff, is they have what's called sensitive or quick clay. Basically, it's this clay that is very strong, but then as soon as anything hits it or any failure occurs, everything just turns to mush. Like, so it can be very misleading. It looks like a strong clay, but then if anything happens, like triggering, then the whole thing will collapse. And what that ends up doing is producing some of these massive landslides that I don't know if it'll work. Let's just see if it actually will load up. And they're pretty crazy. They still have these that occur. All right, boo. So where we may see like some of these, sorry. Yeah, let's go, buddy. You can see, no, hold on. What's going on, dude? Okay. Some of these things, instead of like these just little isolated landslides, since this is a full geologic condition that is moving, the whole, like, yeah, see that? So we have a house over there. This one's from 1970, I think, but we still have a lot of these issues happening in Norway and just Scandinavian countries. This is isolated to areas where there were previous like glaciers and everything. Just in case, I'll show the beginning video again. You can see it's just a full like landmass that slides down. And the issue is when this slides down, then the section above that will start sliding down, and it's a progressive failure that leads to the very top. So again, this is a large scale issue. Like, we're not talking about a project site, but still a better characterization of the soil conditions or that geologic condition in Norway could have at least maybe warned people, or I don't even know how you would like fight against this kind of thing. But still, the knowledge of the soil conditions could lead to a safer management of the land. Yeah, technically it is, but the soil goes all the way to a harder bedrock, so it just scoops it all. Yeah, so I'll leave links to this if you want to learn more. This is again called quick clay or kvik. I don't remember how you say it in Norwegian, but you just can Google Norway quick clay, and that'll pop up. And they still have some issues with that. Okay, so let's see what else. So this is another one that's interesting. This one hits a little bit closer to home in Louisiana, and you guys may have seen this on the news too. This is another due to a poor geotechnical investigation from actually the mining side of things. They were drilling down and didn't realize that they were poking an existing mine 1,000 feet underground, a salt mine. So when they were drilling this exploratory boring, they actually connected this lake to a 1,000-foot deep cavern, a salt mine. So of course, when that happens, that direct connect just causes everything to drain, and it's ends up being a massive sinkhole, and it's pretty gnarly looking. Let me see what happened here. Yeah, so this one, plus you hear these rednecks freak out, which is kind of fun.
Yep, I got it. I got it.
can see pretty gnarly. And again, with these issues, like these are progressive failures. So one like exploratory boring in the wrong spot, just a hole, 12 inches in diameter, can then cause these massive issues where everything is progressive. And they ended up having to like evacuate a whole town for this. Yeah. No, it depends on the type of project, like the sensitivity. If you're in an area where this could potentially happen, then yeah, you may need to do that. Of course, this is very specific. Like there's not salt domes, there's not salt mines everywhere. But in this area, they knew this could have potentially happened. So maybe they should have looked more into it.
Do they know what's going on right now? They hit a cave 1,000 feet down.
Yeah, basically when they hit it, they realize it and then they're, oh crap. So I think this happened in like 2013 or something. Yeah, okay. So this is still ongoing and I don't know if it's stabilized completely yet, but you can go on Google Earth and like see this lake just growing and growing. And then the town ends up being evacuated, and it's kind of a bummer because these are all just good old country folk getting knocked out of their land. Okay, let's see. What else there was one other one I wanted to share. Yeah, because the mine isn't filled with water. So it's so deep that the water all that soil is filling that cavern. So eventually that cavern is going to fill and then it'll stabilize. Right, yeah. Oh, this one is actually, hold on. Another issue that we don't have too much here in Florida, thankfully, but let's see. Right, shaky hands, dude. Let's see if this will work. Is sand liquefaction. So this is an interesting geotechnical phenomenon too in earthquake prone areas. And this one was in the Christchurch in New Zealand. This is so funny. First of all, I just want to pause it. I just think that's the sketchiest thing ever. Still got to get to work or whatever, but just pushing her child up. But this is where actually the soil, when it's under an earthquake, will act like water. And whenever it stops, it will freeze everything. So here, like, that's dry soil that those cars are trapped in. And they have to dig out their cars. So again, during these high earthquake areas, this soil will liquefy. And then whenever it stops, it traps everything. So again, this is a natural hazard. Like this is something that is not the geotechnical engineer's fault. But they still could have done a better job of learning how to densify the soil or remove the soil that could potentially liquefy, so you don't have issues like this. So again, very diverse like discipline of engineering where you have all these natural geohazards. Not only do we have like normal variation in soil conditions, but we have these extreme examples and a lot of area for research. Like there's a big area in liquefiable soils, a big area of understanding quick conditions like the Norwegian clays. So it's still a discipline that is growing a lot over time. All right, how do I get out of here? Okay, sweet. So let me go back to this where I can actually see it. Yeah, so all that to say, like, again, like, in my opinion, being biased, being a geotechnical engineer, it's one of the most rewarding disciplines within the civil engineering because knowing that everything that you're doing is needed for all types of structures. Like as you start working in land development, in wastewater and anything, everybody will have to go through a geotechnical engineer to understand the site conditions. It's also very relatively young science. So 1943, actually, like it was a mechanical engineer from Austria who was like, hey, like, let's understand the mechanics of soil in a little bit more detail. So he was actually the first geotechnical engineer, and he was a mechanical engineer, but we'll forget about that. But not until 1943, so it's still a very relatively young science. It's still a very relatively young discipline of engineering. So there's still a lot of development and a lot of area that we can improve. And there's a lot of behind the scenes of some of the largest structures and landmarks. So it's kind of cool to see that. There's this quote, I think it's by this guy, but he said, the same guy who founded it, there's no glory in foundations because most of the work is buried. So if you like knowing the behind the scenes stuff of structures and like what the rest of the public doesn't see, like conspiracies and stuff, then this is your area of discipline of geotech. So I'm excited to go through this all throughout the semester. I hope you guys enjoy it. Yeah, we'll start next week where we start talking about the introduction of what makes up soil and how we can use it as a construction material. So enjoy your weekend. Thanks for coming early in the morning. I'll see you all next week.